Every megaproject begins with one question. Can engineering permanently connect these two distant shores? The first stage is decision-making, where experts determine whether an underwater tunnel is truly necessary and achievable. The engineers first study existing transportation systems, traffic congestion, population growth, shipping activity, and future demand. Computer models help planners determine where the tunnel should begin, where it should end, and how long it must be. Economic specialists estimate construction costs, operating expenses, expected traffic, revenue, and the project's long-term economic value. A $10 billion tunnel must deliver enough transportation and economic benefits to justify its enormous investment. Before construction begins, authorities must secure public approval, regulatory support, and confidence in the project's long-term benefits. Once the project receives approval, engineers move from planning into detailed investigation of the proposed route. The first major technical challenge is understanding exactly what lies beneath the ocean floor. Advanced sonar systems scan the seabed and reveal underwater valleys, sediment layers, rock formations, and possible geological hazards. Survey specialists combine sonar measurements with satellite positioning to create an extremely accurate map of the tunnel corridor. Survey boats repeatedly cross the proposed alignment because even small errors can become serious problems underground. Geotechnical teams then drill deep into the seabed to discover the strength and composition of underground materials.
Long rock cores provide engineers with physical evidence of the underground conditions they must eventually tunnel through.
Scientists test each sample for strength, water absorption, fractures, mineral composition, and other properties that influence tunnel safety. The results are combined into a detailed geological model showing where strong rock, weak sediments, and groundwater may exist. Engineers use this geological model to select a depth that provides both structural stability and protection from the ocean above. Seismic surveys help identify hidden faults, weak zones, and geological structures that conventional drilling might miss. Every discovery changes the risk assessment and helps engineers refine the safest tunnel alignment.
Engineers must also understand the marine environment before construction can disturb the seabed.
Marine scientists document sensitive habitats, fish populations, migration routes, and ecosystems that must be protected. Environmental data determines where construction activity can occur and how ecological damage can be minimized. The final route must balance engineering requirements, environmental protection, transportation needs, and construction cost. With the route established, engineers begin designing the tunnel and every system required to keep it safe. The design includes the tunnel structure, lining, emergency passages, ventilation, drainage, electricity, communications, and fire protection. Engineers simulate pressure, movement, vibration, flooding, fire, and extreme conditions before construction begins. The deeper the tunnel goes, the greater the pressure, making waterproofing and structural strength absolutely critical. Engineers must choose the construction method that best matches the geology, water depth, environmental conditions, and project budget. For a bored tunnel, one of the world's largest machines must be manufactured specifically for the geological conditions. Hundreds of hardened cutters will eventually grind through rock deep beneath the seabed. The completed machine can stretch for more than 100 meters and weigh thousands of tons. Transporting the machine to the construction site becomes a major engineering operation of its own. Meanwhile, construction teams prepare the shore facilities needed to support years of continuous underground work.
A deep launch shaft gives the tunnel boring machine access to the underground route.
The shaft must be strong enough to resist enormous ground pressure and support the machinery entering the tunnel. High-strength concrete forms the foundation of the launch infrastructure and the tunnel's supporting structures. After assembly, the giant boring machine is carefully lowered underground and positioned for its first advance. Then the machine comes alive. rotating its cutting head and beginning the long journey beneath the ocean. Powerful hydraulic systems push the machine forward, while the rotating cutters break the surrounding rock into manageable pieces. The excavated material is continuously removed through conveyor systems, so tunneling can continue without stopping. Behind the cutting head, every meter of newly created tunnel must immediately be stabilized.
A robotic erector places massive concrete segments around the tunnel to create its permanent structural lining. Each segment locks into the next, forming a continuous circular ring capable of resisting surrounding ground pressure. Inspectors examine every ring for cracks, alignment errors, damaged seals, and other defects before tunneling continues. Watertight gaskets between the segments prevent groundwater from entering the finished tunnel. Engineers inject controlled grout behind the lining to fill voids and stabilize the surrounding ground. Hundreds of sensors continuously monitor the machine and surrounding ground while excavation progresses.
Precision surveying ensures the machine remains exactly on its planned alignment beneath the ocean.
Geology can change unexpectedly, forcing engineers to adjust machine pressure, cutter settings, and excavation speed. Every excavated material sample provides new information about the underground conditions ahead. If groundwater appears, powerful pumps and sealing systems control it before it can threaten the excavation. The machine must periodically stop so crews can inspect, repair, and replace components exposed to enormous forces. Worn cutting tools are replaced to maintain excavation efficiency and prevent unexpected machine failures.
Thousands of tons of excavated material are continuously transported away from the tunnel face.
At the surface, the excavated material is processed, transported, reused, or safely disposed of according to environmental requirements. Where possible, excavated rock can become construction material, reducing waste and lowering the project's environmental footprint. Thousands of specialists work in shifts because a mega project of this scale must operate continuously. Safety remains the highest priority because every worker operates inside an environment surrounded by immense geological forces. Emergency refuge areas provide protected spaces where workers or passengers can shelter during a serious incident. Ventilation shafts and powerful fans are designed to control air quality, heat, smoke, and emergency conditions. The ventilation system must move enormous volumes of air through a tunnel stretching beneath the sea. Drainage systems collect controlled groundwater and accidental water entry before it can reach transportation areas. Additional waterproofing systems create multiple layers of protection against the surrounding groundwater. Electrical systems provide power for lighting, ventilation, communications, monitoring, and emergency equipment. Thousands of lighting fixtures transform the dark underground passage into a controlled and visible transportation environment.
Fire detection systems are positioned throughout the tunnel to identify dangerous conditions as early as possible.
Specialized suppression systems provide rapid response if fire ever threatens equipment or passengers. Communication systems allow operators and emergency teams to communicate with people inside the tunnel at any moment. Continuous surveillance allows control centers to detect unusual activity, stopped vehicles, smoke, or other hazards.
A centralized control center monitors the tunnel around the clock and coordinates responses to any emergency.
If the tunnel carries trains, the next stage is installing the track and precision railway infrastructure. Rails must be aligned with extraordinary accuracy to provide safe, smooth, high-speed transportation.
Power distribution and signaling systems are then connected to the tunnel's transportation network. For a road tunnel, specialized paving systems create a durable surface capable of handling enormous daily traffic.
Every lane, barrier, drainage channel, and emergency walkway is installed according to strict safety requirements. Emergency passages and reinforced doors provide alternative escape routes if the main transportation area becomes unsafe. After years of excavation, the two sides of the project finally approach the most important moment: completing the connection. Surveyors make final measurements because the two underground sections must meet with extraordinary precision. Even a small alignment error could create structural and transportation problems, so every measurement is checked repeatedly. Then, after years underground, the cutting head finally breaks through, and the tunnel becomes one continuous passage. For the construction teams, the breakthrough represents years of risk, precision, sacrifice, and engineering discipline.
But structural breakthrough does not mean the project is finished. Thousands of final construction tasks remain.
Robotic inspection systems examine difficult areas and search for defects that human crews may not easily see. Permanent structural sensors are installed to detect movement, vibration, temperature changes, and water pressure throughout the tunnel's life. Every joint and seal is inspected because long-term resistance to groundwater is essential beneath the ocean. Drainage and pumping systems are tested under controlled conditions to ensure they can handle unexpected water infiltration. Ventilation engineers test the system at full capacity to verify that air and smoke can be controlled during emergencies.
Emergency responders rehearse realistic scenarios so they can act immediately if an incident occurs after opening. Medical teams practice evacuation procedures because even seconds can matter during a real emergency.
All systems must work together before the tunnel can safely carry passengers.
The first test vehicle enters the tunnel to verify the transportation system under real operating conditions.
Engineers measure speed, vibration, braking, communications, ventilation, and electrical performance during test runs. For a road tunnel, controlled vehicle tests verify traffic flow, lane safety, visibility, braking, and emergency response. Engineers verify every clearance because even small dimensional errors can affect safe transportation. Normal and emergency lighting systems are tested repeatedly to ensure visibility remains available during power failures.
Backup generators and emergency power systems must automatically keep critical equipment operating when the main supply fails.
Communication networks are tested from every section of the tunnel to guarantee uninterrupted emergency coordination. After years of construction and testing, the entrances are finally integrated into the surrounding transportation network. Final inspections confirm that construction quality, safety systems, environmental requirements, and operational standards have been satisfied.
The project now reaches its final milestone, opening the tunnel to the public.
The first public journey marks the moment when billions of dollars of planning and engineering become a working transportation connection. Passengers can now cross beneath the ocean in minutes through infrastructure that took years to create. Above the tunnel, ships continue crossing the ocean, while an entire transportation system operates silently below them.
Once operational, the tunnel becomes a living system that requires constant monitoring and maintenance.
Maintenance crews regularly inspect the structure, equipment, electrical systems, drainage, and ventilation to prevent small problems from becoming major failures. Robotic systems can inspect difficult areas while reducing the need to expose workers to hazardous conditions. Continuous monitoring helps engineers detect subtle changes before they become dangerous.
The completed tunnel reduces travel time, improves trade, connects communities, and transforms the regional economy. Its impact extends beyond transportation, strengthening commerce, employment, tourism, and regional connectivity. Hidden beneath the ocean, the $10 billion tunnel stands as a remarkable achievement of planning, science, technology,